¿Listo? Listo. Buenos días. Acá estamos en el seminario de ciberseguridad. A continuación, viene la exposición del profesor Rafael Khoury. Ayer el profesor Alberto Mayor indicó una exposición de la parte estratégica del tema de la ciberseguridad. Hoy día vamos a ver de la parte táctica de la ciberseguridad. Vamos a exponer patrones, vamos a exponer sentencias, de tal manera que las personas, el líder, el comandante, tenga herramientas para poder auditar, hacer una autopsia de los software que pueda requerir y de tal manera que pueda decir por qué están estos tipos o por qué no están a un desarrollador final. De tal manera asegurar la calidad de los productos y con ello poder asegurar la seguridad de su institución. Con ustedes, el profesor Rafael Khoury.
De Quebec.
De la universidad, discúlpeme, el profesor Rafael Khoury es de la Universidad de Quebec, es experto en ciberseguridad, ha participado en proyectos con el Ejército de Canadá, actualmente es director de un proyecto nacional, federal, del gobierno de Canadá para la ciberseguridad de instituciones financieras, es representante de la Universidad de Quebec para todos los temas de investigación con Latinoamérica, y es una persona relevante en el tema de la ciberseguridad a nivel mundial. Gracias, profesor Luis Molina. Gracias, buenos días, Rafael.
Gracias, buenos días y gracias por invitarme. Es un placer de estar aquí y de hablar con ustedes. Voy a compartir mi screen. ¿Ustedes me pueden decir si ven mis slides?
Sí, perfecto.
Perfecto.
Sí, gracias. Mi presentación estará en inglés. So good morning. It's really a pleasure to be here with you today. So I'm Professor Rafael Khoury. I'm a professor at Université de Quebec in Chicoutimi, which is in northern Canada. But actually starting this fall, I'm changing university. I'll be a professor at Université de Quebec in Outaouais, which is in our country's capital in Ottawa. So today I'd like to talk to you about a very particular class of vulnerabilities. And these are vulnerabilities that are introduced during the compilation process. So you write code, software source code, and it's compiled into binaries. And you'd expect that the binary is conformant with the source code that you wrote, but that's not exactly always the case. And sometimes small changes will be introduced in your code by the compiler, and this will lead to vulnerabilities. So I'll explain how this will happen. So first, I'd like to introduce you to this essay by Ken Thompson. Actually, it's a speech that he gave that was published in an essay. It's very accessible, and it's actually well known in the computer security field. It's called Reflections on Trusting Trust. So Ken Thompson remembered that when he was a student, his fellow students and him would try to write a program that when you run the program, it creates a copy of itself. And the goal was to try to make it as small as possible and compete with that with his fellow students. Well, taking his idea a little bit further, he asked, if you can write a program that can copy itself, can the program create a copy of itself, but with some changes in it, maybe with an added vulnerability? And then he takes the idea just one step further and he says, what if the program that we have is a compiler? And when you execute it, so you compile a program with your compiler, so you run your program, it compiles the source code, but it adds a vulnerability in the code. And then the compiler copies itself and removes from itself the little bit of code that introduced the vulnerability. So you have a schema that looks like this. You have the initial source code that you want to compile. You have a malicious compiler. And when you compile it, well, it creates a contaminated binary. The idea is that it could create a binary code with a backdoor, maybe. When you log in, enter your password, and instead of just saying, well, if the password is correct, you enter. Well, if the password is correct, or if some hard-coded value is entered as password, you can enter. But then the compiler copies itself, creates a new copy, and deletes the previous one. So if you examine the compiler, you don't see anything unusual. If you examine the source code, you don't see the vulnerability. It's not present there. It's only present in the contaminated binaries. And it's very hard to examine binary code. So it's a very malicious vulnerability, if you will. So that's a thought process that makes you think about what are you trusting when you trust that the program is secure. That's why the title of the paper is Reflections on Trusting Trust. And usually we trust that the compiler will produce source code that is conformant, will produce, binary code that is conformant with the source code. But that's not always the case. And that's the topic of this presentation. In fact, in this presentation, I'll go through a number of optimization or changes that the compiler can perform. And I will show you how these will affect the security of your code. And I'll talk about countermeasures also. So let's start with clearly stating the problem itself. I'll go through 4 or 5 slides with theoretical underpinnings of what we're talking about, and then I'll give some examples that will make this much clearer. So the problem is that compilers are becoming increasingly aggressive in the optimization that they perform on code in order to produce binary code that is optimal in time, execution time, and space. But this optimization can transform the source code into something that is not truly equivalent. And there are 2 concepts that are critical to understanding this phenomenon: the language specification and the concept of undefined behavior. So I'll explain each of these. So languages like C and C++ and any other language actually usually have a specification. The specification is sort of contract between the programmer and the compiler. If the programmer writes code that is conformant with the specification, then the compiler will produce code that is consequent with what the programmer wrote. So the specification of C and C++ specifically is extremely complex, very inaccessible even to an experienced programmer. It looks like a text of law, and that's why I actually showed you an extract right here at the bottom of the slide. So it says, what this slide says, this example here says is just from the spec of C, and the section and subsection and subparagraph, like a text of law. And all that is just to say that if you add 2 pointers, the result is also of type pointer. The spec even specifies things like if you add 2 number, the result is the sum. So that's also in the spec. So very precise. But there's a few cases in the spec where some behavior is actually not specified, and it's called undefined behavior. There are 3 cases where this happens. The 3 cases are interchangeable. So there are cases in the spec where it says this is undefined behavior. Accessing a pointer to memory that has not been initialized is undefined behavior. There are cases where the spec says this shall happen or this shall not happen, and if you do the reverse, it's undefined behavior. So the spec says that if you allocate a memory space of size 0 and you try to use it, you shall not use this memory space. And the other case, the 3rd case, is if something is just omitted from the spec. So you go through, it's 1,000 pages, you go through the entire spec and you don't find some particular case that you're looking for, so that means it's undefined behavior. And these 3 definitions are interchangeable. There is no general definition of, no complete list of what is undefined. In the spec of C, in the annex, there's a partial list, but it states that it could be incomplete. And C++ is just no list. Here are some examples of undefined behavior. Dereferencing a null pointer, this we're all familiar with. It throws an exception, but it doesn't have to free the same memory twice, use memory that hasn't been allocated right outside of a buffer. Overflow, this one we'll get back in a moment. Unassigned integer, if you go over the maximum value and it rolls over, comes the minimal value. Division by 0, there's many other. Now, it's the job of the programmer to ensure that undefined behavior does not occur. The compiler just assumes that undefined behavior is impossible and does not occur in the program. So what happens if undefined behavior does occur? Well, the program might act unpredictably, the execution might halt. That's what happens when you dereference a null pointer, but it really doesn't have to. As far as the spec is concerned, undefined behavior means that you could, any behavior is possible. In fact, there's a very famous quote in the field of compilation from John Wood. I copied it here. When the compiler encounters undefined behavior, it's legal to make demons fly out of your nose. It's a very funny way of seeing it, but what he means is any behavior is possible if undefined behavior is encountered by the compiler. And we'll see cases where some really weird things can happen. So there are two little related cases, two little cousins of undefined behavior, unspecified behavior and implementation specific behavior. So the first one, unspecified behavior, means that the compiler gives several choices to the, the specification gives several choices, and the compiler must be consequent with one of these choices. So malloc 0 is the best example of unspecified behavior. Malloc 0 means you request a memory of size 0. If you do that, well, the compiler can't do anything it wants, but it must do one of the following two things: either return null or return an unusable memory space. So a pointer to a space of memory that the programmer is not allowed to use. And in fact, it says that if the programmer tries to use that memory space, well, that is undefined behavior. And implementation specific behavior is behavior where the compiler just states how it will behave and must always be consistent with itself, basically. So the best example of that is the size of all the basic types. So how big is an integer? How big is an int? It could be 4 bytes or it could be 8 bytes. The compiler states that. And then the compiler is always specific, always consequent with that. So with those two cases, you don't have always the same problems as with undefined behavior, but you might have a program that runs well and you test it, it functions well, but then you recompile it on a different platform and it no longer works. That's because you had undefined behavior or implementation specific behavior. So it's important not to depend on that. Now let's get back to undefined behavior, which is the core of the problem. The compiler has a rule called the as-if rule, which states that it can perform any optimization as long as the final result of any computation is the same as it would have been without the optimization. So the final result means the result of the computation and the side effects. Side effects are stuff that's printed on the screen or sent on the network and so on. But undefined behavior is not part of side effect or the results. It's treated as something that can't happen, so it can be optimized. So this was fairly theoretical, so I'm going to give an example of how this would work in practice. So consider this really simple code here. We have an integer. If it equals 0, it's not supposed to equal 0, so there's a e-report and we're an error message. It doesn't say here, but we're going to suppose that this e-report function terminates the execution. So it never returns, there's a typo here, it's return. It never returns to the final line. So the compiler sees this, but we didn't specify that e-report doesn't return. we could have. There's a keyword in C++, no return, that says if you call a report, the next line is never executed. Or we could have had if equals 0, a report, else return. We didn't do that either. We just have a report. If we examine the code of a report, we'll see it doesn't return, but the compiler doesn't know that. So what will the compiler do if it sees this code? It'll reason as follows. After you return from a report, there's a division, and argument 2 is the denominator here. But the division by 0 is undefined behavior, and undefined behavior cannot happen. The compiler assumes that undefined behavior can't happen. So arg2 can never be equals to 0. So if you compile this code with some compilers, and this varies by compiler, but it's very likely that you'll see that there's no if, there's no comparison, there's no call to e-report. All there is in this place will be return the result of the division. The compiler assumed that division by 0 is impossible, and so it assumed that this if can never take place. So the compiler removed a test and a function call from your code. Let's say now another example that's more closer to security. A very common optimization is dead code elimination. So dead code elimination means if the compiler sees that some computation is never used, well, why make this computation? Look at this example here. We have a function call. Then inside the function, there's a division. The result of the division is assigned to this variable z here. And then it returns something else, a multiplication. So why do this division? Why do the store? It's useless. It's not observed. It's not used elsewhere. So, and this is for any compiler, basically. This division will be, this line will be removed completely if you examine the binary code. So how does that affect security now, which is what interests us? Look at this code here. It's a function to validate that the password is correct. So we load the password in memory, get passwords. There's 64 bytes for the password. There's a verification. I elided it. We don't need to worry about that. But once the verification is correct, you want to remove the password from memory. You don't want to leave the password in memory because maybe something else will read memory later. Maybe there's a buffer overflow or the system hibernates. So memset in the area where you store the passwords, all zeros for the size. You zeroize the memory. This is very good programming practice. I tell my students, whenever you load the password in memory, when you're done with it, you zeroize it. But what happens when the compiler sees this? Well, the compiler will very likely see this and say, well, this is writing to memory that you never read. So it's dead code, and the compiler is quite likely to delete this line. So you write a security check, and the compiler removes it. And this exact vulnerability was found in tar. Tar was, it's an old program to write archives, create archives like zip and rar, RIR. And so you'd create an archive, and if the file you put in the archive was smaller than the size of the compressed file, there was trash, like junk memory in the file, and you would send it on the network with that. And there could be bits of the shadow file that contains all the passwords in the archive that you would send to someone else. So that was very, very dangerous. You'd wonder how a vulnerability like that could be in a program like tar. And the answer is, well, the vulnerability wasn't there on the initial release of the program. At some point, someone updated the program, made a patch for some other reason. It might have been just optimization of memory usage or reordering the way that things are methods are called, and that created the vulnerability. And I think that shows how subtle and difficult the problem of security is. It might be that the vulnerability initially was not present because there was some memory intensive operation being performed after you read the passwords, and then they just optimize these operations or moved these operations, and then you had the vulnerability. So how do you protect against that? There are several solutions, none of which are perfect. I'm going to move this a little bit. And so I'm going to go rapidly through all the possible solutions. One of the solutions is function zero memory. It's present on Microsoft environments only, and it might be optimized just like memset. There is a solution, good solutions that can't be optimized. Secure zero memory. This is a function that's also only available on Windows. It's a part of Windows.h. But if it is available, it can't be optimized. It's a spec of that function, so you can use that. This is the syntax at the bottom. Since C++11, there is a function called memset_s with the same functionality. So that's universal. It's a part of the spec of C++. It can't be optimized out. The problem is, first of all, it's an optional requirement, an optional part of the spec. So some compilers might not carry it. And also, a very large part of our security problems is old code. Now you think C++11, it's 2011, it's recent, but actually we still have code that's much older than that in C and C++ that's run widely, libraries that are still used, and we still find vulnerabilities in this old code. So it might not use memset_s. So this is the best solution if it is available. I'll go through just some other possible solution quickly. Pragma is a part of the spec to send commands to the compiler from the codes. And one of the commands that you can send is to turn off optimizations. So this is the syntax, I put it at the bottom. Pragma optimize, a list of optimization, and then you turn on or off. This is a typo, it should say on. So the way it works is here with this line, we turned off, in this case, all the optimizations because it's in quotes, or we could have specifically turned off that code elimination, and then you perform the memory write, and then you would turn it on. This should work. Actually, if you're going to use that, you might as well turn off completely that code optimization. It's not a big optimization, and it's something the programmer can do by himself. The problem is, we say this would work if the compiler is consequent with the spec. And it seems that Pragma is one case where sometimes the compiler is not consequent with the spec, and it might ignore the command. I'll go quickly on this. There's another solution that's suggested by a writer called Robert Secord. So one thing that could be done is the keyword volatile. The keyword volatile is there to inform the compiler that some memory, some variable can be modified by something that the compiler doesn't see. So in this case, if you mark a pointer as volatile, it means that the value pointed by a pointer, PWD, could be modified or could be used or read by something outside the control of the compiler. So the result is that, well, the compiler must assume that after setting the memory to 0, something else might read it or write to it, so it won't do the optimization. This might work, it might not always work. I tried it actually, and for me, depending on how I compiled it and which compiler and which compiler flag, sometimes it worked, sometimes it only protected the first byte, and the rest of the buffer was modified. So it's really useful to try these out and look at the compiled code with the decompiler and make sure that it really does what you want it to do. Erasing a password from the memory is actually fairly important. So for defense in depth, another thing you might do is later in your program, if you create an object that you're going to send on the network or write to a file, you create your object, initialize all the memory to 0, even if you know you're going to write later to the object. That way, if there was something in those memory spaces, well, you've initialized it to 0. So if it was present, it's not present anymore. So let's look at another example of another security problem that's related to an optimization. And I'd like to start with the case of a vulnerability called JPEG of death. Very evocative name. It's actually a fairly old vulnerability, but it's still used in computer security because it's a really textbook example of a particular problem. So inside the JPEG image, there's a comment field. It's an optional comment field. I think most people don't even know it's there. But you could write a little bit of text that describes an image and include it in a JPEG. It was there in case you want to put copyright associated to a JPEG. And so if it is present, there's a data structure that contains the string, but without a string termination character, and the size of a string in a short. And the short itself is 2 bytes. It's the size in bytes. So what happens when you load a JPEG into memory? There's a bit of code that looks like this that's executed. So the code will get as parameter the length that you want, as I said, the length of the comments, and a pointer to the comments itself. Now recall that it's the length of the comment plus 2, because the length itself is the size of the short that contains the length is included in that number. So the code will load this into memory. Start with length minus 2 to get the exact length of the comment field. Then it'll reserve memory for that size plus 1 for the null terminating character. And then it'll copy from the source to the destination so many characters. So where's the vulnerability here? I suspect some of you might have guessed the vulnerability. So the thing to understand is that the minimal value for length is 2. If there's no comment, the length of the comment field, if the length is 0, well, len here has to be 2 because it includes the length of the short itself. But what happens if you create a malformed JPEG where the value of length is 1 or 0, in this case, length 1. So let's go through the same segment of code, but len is equal to 1. So you load into memory, len minus 2. What does that do if len is equal to 1? Well, it rolls over to an extremely large value, the maximal value of this data type. For unsigned int, it's 4 billion. Then allocate memory of 4 billion plus 1. It rolls over again, and you allocate size 0. I mentioned earlier, if you allocate size 0, you might have a null pointer, or you might have a pointer to unassigned memory that you're not allowed to use. And that's what happens in this case. So you have a pointer to unassigned memory, and you try to write it, you'll override. This will actually throw an exception. The program will crash, it'll throw an exception. The program will get back on track, but the memory has already been corrupted at that point. This is called the unlinked vulnerability, if you want to read about it. But how it's exploited is not really relevant for this discussion. The important thing is, because you go over the maximal and minimal value of your data type, you have a vulnerability here. And it's a very important class of vulnerability called integer overflow. Now, imagine now that the programmer is aware of this problem. The programmer might write a test to a check, basically to protect himself. So here's another example. We have a pointer to the start of an array, or a pointer to the end of an array, and you want to write at a certain offset, len, or a certain number of characters. So before you write, a prudent programmer writes pointer plus len if it's greater than the maximum? Well, it means there's more characters here than I can write on the array. So to prevent, this is just to prevent a buffer overflow actually. Len is too big, return error, don't write. So that's a basic test that you learn in security to protect against buffer overflow. Now, the thing you realize is if pointer plus len, pointer is a very large array and len is very large and pointer is high in memory, so this might overflow. A pointer is still basically an int, maximum value 4 billion. So if pointer plus len causes an overflow, an integer overflow, you have a situation where pointer plus len is a very small value because you went over the maximum value of an integer, and then this test will succeed and you'll be able to write in the array even though you're vulnerable. So the programmer is aware of this. So the programmer writes a better test to protect himself. So instead of this test here, if pointer plus len is greater than max, return error, we have a slightly more involved test. If pointer plus len is smaller than the pointer, well, we had an overflow. Or if the pointer is greater than len, then len is too big. So it's a very reasonable security test, but here's the problem. The compiler assumes that integer overflow cannot happen because integer overflow on signed integers is undefined behavior. So the compiler might have the following reasoning. Pointer plus len smaller than pointer if len is verified that len is positive before. Well, that's impossible. That's mathematically impossible. The only way this could happen is if an integer overflow takes place. An integer overflow is undefined behavior, so it can't happen. So the compiler might delete this test, the left half of this test, and you leave only the first. And this actually happened in Linux code. And CERT, CERT is an organism that does security notices and distributes security information, issued a vulnerability note against the compiler. And there was a little war of words between the Linux programmers and the compilers. The Linux programmers said, well, you deleted a security check that's essential, and GCC is vulnerable. But actually, the GCC programmers said, no, we're consequent with the spec of C++. C++, the spec says, undefined behavior cannot occur, and it's the job of the programmer to make sure it doesn't. And the compiler assumes it doesn't happen. So technically, GCC was correct. And almost the same problem happens in the following example. Here again, we have a buffer. We have something we want to write in a buffer. Let's assume the buffer has a fixed size, 100. So you want to test if there's an overflow that's possible. So you try to test if buffer plus what the size that you want to write is smaller than buffer plus 100. Actually, the compiler will replace this with n smaller than 100 because the compiler makes a very simple arithmetic simplification. Buffer plus n smaller than buffer plus 100 is the same thing as n smaller than 100. There should be a space here. So, and mathematically, this is logical. We learned this at school. But this test is really useful in case an integer overflow happens and the compiler doesn't consider that. So this is actually frequent enough that there's an entry in the CWE database. CWE is a list of all sorts of vulnerabilities. So compiler optimization removes security critical code. That's CWE 733. So the following tests would fix the problem. Instead of pointer plus len smaller than max, you should try if len is greater than max minus the point. That would work. Other things you can do to protect yourself, use unsigned types. I'll explain to you in a moment why unsigned types are safer. Well, because overflow is permitted on them. There's also special types that are part of the spec of C++ that can help protect you. R size T is guaranteed to be sufficiently large for most uses that you won't have an overflow. And ptr_diff_t, that's a type that's specially made for pointer manipulations that it can't overflow if you add or subtract 2 pointers. So you should use those. Those are actually implementation specific types. So they'll change from one compiler to the next, but they will always be big enough to avoid the problem, or at least to avoid the problem in most cases. So I mentioned unsigned types are safer. So signed types are the one that can have a negative or a positive value. Unsigned types are only positive. In C and C++, overflow for signed types is undefined behavior, but overflow for unsigned types is permitted. It wraps around, so you reach the maximum and you roll to a negative value, to the smallest value, which is 0. And so tests on the same types of tests that we saw earlier, if every variable is unsigned, the compiler will not remove them. It's well defined in the spec that it rolls over and reaches the smallest value of 0. So it is well defined. So in principle, you could use it, but it's better not to. And I'll show you an example why. So this is code from a paper by a writer called Dietz, who studied this problem closely. He wrote several papers on this topic. And so this bit of code is a random number generator, an algorithm called the congruent linear generator, which is one of the most widely used algorithms for simple things, for non-security relevant things. And the final step of generating a random number here with this algorithm is to wrap over the maximum value in the range. So one easy way to do that is to use the overflow of an unsigned int. So that works. It's well defined. It'll behave as expected. But recall that the size of the basic types, the size of int and long and double, is implementation specific. So it might work on one platform, but if you use the same code on a different platform, this might not work, because the size of the basic type might change from a 4-byte int to an 8-byte int, for example. There's really no guarantee on the size of basic types. So Dietz calls this a time bomb. This works for now, but it might not work forever. Another example of undefined behavior and how it might affect security is dereferencing a null pointer. So the null pointer is equal to 0. 0 is not a valid address. If you try to access address 0, there's an exception. The C guarantees that null is always equal to 0. But dereferencing null is undefined behavior. How does that affect security? And now we have another example of Linux codes. What happens here? Here we have a little function that tries to use the value pointed by pointer b. So if b is null, there's an exception that's thrown here at that line. 2 lines later, we test if b is null, and if it's not null, we continue. So the compiler sees this and has the following reasoning. Well, if b is null, there's an exception here. So this test will never be true because nothing in between modifies the value of b. So this test is redundant. Delete it. And if you examine the compiled code for this fragment of code, you'll see that the test might be absent. Again, this varies from one compiler to the next. Here's the problem. In some embedded systems, 0 is a valid value. And there are attacks that take advantage of this fact. And this test was needed for security relevant things. So when you deleted it, if p was 0 and it was a valid value in an embedded system, well, then you have an exploitable vulnerability. There's actually a long blog post by Linus Torvalds, who is the creator of Linux, that discusses this fragment of code specifically. And the main thing he says is, when you compile Linux with GCC, there's a flag, I copied it here, like f no delete null pointer check, that basically tells the compiler, I don't want this optimization. Do not remove redundant null pointer checks. And it's because of this case and other cases like this. And it's not like this is a very critical optimization, like the pointer check takes a microsecond. A final example, and there could be others, but I decided we can conclude with this one. There's a function, standard function called memcopy. I think we've all used memcopy if we've coded in C++. And something that we might not know is that memcopy is not defined if the two buffers that you copy overlap. So that's something you just have to know. Memcopy is undefined behavior if you copy from a buffer to a destination that overlaps. So this is the very commonly used gzip program. It needs memcopy. The programmer knew that the buffers might overlap. He knew that memcopy is undefined when the buffers overlap. So there's this test here. Here is the number of bytes to be copied. W and D are the source and the destination respectively. So he tests if they might overlap. Well, in that case, memcopy is not used. There's the if they don't overlap, you use memcopy. That's what's there. And there's an else. You use a slower memory copy function whose name escapes me right now. The problem with this is the programmer assumed that W was always lower in memory than D, and there's no reason to think that. So it was actually possible for two buffers to overflow, and then memcopy is undefined. You might copy something and then overwrite what you just copied, and this exposes you to buffer overflow attacks. So I like this example a lot because several reasons. First, the vulnerability remained in gzip for 17 years. And that shows you how subtle security is. Another thing that shows how subtle security is the fact that many people don't know that memcopy can't be used if the two buffers overflow. That's a really specific thing to know. We don't normally teach that to students. And I believe that in order to write secure code, you have to know a lot of these really tiny details about the languages that you use. Sometimes you see those books, learn language X, learn Python in 24 hours. And there's 24 little lessons of 1 hour, and then you're supposed to know how to code Python or Java or whatever. I believe this is very dangerous from the point of view of writing secure code, because writing secure code, especially in C and C++, there's a lot of tiny little implementation details that you need to know about in order to write securely. Another fun fact about this example, so there was a solution. The solution was to replace the line here with this line in red, and that works. That's a complete solution, but it's suboptimal. In some cases, the slower function will be called, even though memcopy is risk-free. So the real best solution is the one in green at the bottom of the slide. However, it's a bit hard to follow. And in security, it's useful to aim for simplicity. Harder code that's more complex is harder to maintain. And then you might have a situation where somebody else needs to modify the code and you might not understand all of that. Oh, I forgot, and yet another example. Using uninitialized memory. So sometimes we use uninitialized memory. We're not supposed to. The compiler sends a warning, but doesn't stop us. So what happens if the compiler realizes that you're using uninitialized memory? Well, it's undefined behavior. And when you use uninitialized memory, the compiler is allowed to remove that reference to memory and replace it with a constant. So a lot of people think that undefined memory has to be 0. It doesn't have to be 0. It can be any constant that the compiler chooses. Not only that, but because the undefined memory can be any constant, any computation that is derived from undefined memory can also be replaced by a constant. So here's an example from FreeBSC. Again, a random number generator. You need a random seed. And the random seed is the process ID mixed with the time of day in microseconds, mixed with undefined memory. And the novice programmer might have thought, oh, I'll get some entropy from undefined memory. But the compiler is allowed to take this entire expression here, junk, exclusive OR, get process ID, exclusive OR, get time of day, and replace all of that with a constant. So we'll always have the same seed whenever we run the program, because any computation that's derived from undefined memory can entirely be removed and replaced with a constant. So you run this code. If you compile this code, you look at the compiled code, all that in the interior might be missing. Even the order in which you apply optimizations might affect the final result. So let's look at this simple example here. This is a bit of a toy example. We have a small function, takes in a pointer, writes this pointer to some dead code, dead variable that's never used, then tests if it's a null pointer. If not, if so, it returns. If not, it assigns a value to it. Okay, so it's a toy example, but it looks a lot like the Linux example we had a few slides ago. So imagine that it does dead code elimination first, and then the elimination of redundant null checks. So it starts by eliminating this. This is dead code. You write, assign the value to dead, and you don't use it. This is the only optimization that happens in this case. You don't know that anything else is a null check. So the final code would be this here, the if, return, and assign for. Now let's do the reverse. Elimination of redundant null checks, and then dead code optimization. Now the optimization will be done in 2 steps. First, the compiler will have the same reasoning that I mentioned earlier, that you're using the value of P. So if P is null, there would be an exception. So there's no point in testing if P is null at the same time. So if it'll be replaced by false, this will be, the test will be removed. It's a redundant null check. So the check is deleted, and then you have if false. So that's that code, that's unreachable code, and the int is dead. So this entire bit will be removed, and all that's left is assign the value of 4 to. Not only that, but if you have a function with only an assignation in it, that will be inline. Inline meaning that it'll be, instead of calling a function, it'll take the code that the function does and replace it where it's called. And that has its own fairly complex security trade-offs. So, and the order in which optimization is applied is not something that's part of the spec, and not something that you can usually control with the compiler. All you can do is turn off optimizations. So now let's talk about countermeasures. How do you protect yourself against this problem? So the main countermeasure, the one in bold, is programmer vigilance. The programmer should be aware of what undefined behavior is, should be aware of all these little fine details of the languages that he used, like the fact that memcopy can't be used on overlapping buffers, the fact that integer overflow is undefined behavior on signed integer, but defined behavior on unsigned integer, and so on. That there are tools that can help, but there's no alternative to the programmer being aware of these tiny details of programming. So the programmer must ensure that undefined behavior is impossible in his or her code. One thing that can help that I mentioned in passing are compiler flags. So I mentioned the second one, no delete null pointer check. It's a small optimization anyway. FWRAPV, this tells the compiler to assume that integer overflow is always possible. So all sorts of optimizations that the compiler might otherwise do become impossible or not permitted in this case. This is how Java works, actually. The other flag you might want to use is called W strict overflow equals, and then the n is a number, 1, 2, 3, 4, 5. And what that does is that it throws a warning to the programmer anytime an optimization takes place in a situation where an overflow is possible. And the higher the value of n, the more warnings you will get. Actually, the more cases are there where the compiler will send you a warning. So use n as high as you're comfortable with. If you're just drowned in warnings, you can lower the value of n. But normally on a project of reasonable size, you'll get not too many warnings, and then you can investigate by yourself. Well, there's a warning there. What did the compiler change? Is this a problem for security? So deleting all these compiler optimization, how does that affect execution time of your codes? Well, there's a study about that, Wang et al. They looked at 12 programs, and they compiled the same program with and without any optimization. And that's like any optimization, not just the security relevant ones. And in 10 of the 12 programs, there was no noticeable slowdown. In 2 of the 12 programs, there was a slowdown of about 10%, but in both cases, the slowdown was localized in a single loop. And by paying special attention to that loop, you could optimize it manually. It was a matter of making sure that the computation is simple enough, the condition is for the loop is simple enough to remain in the cache throughout the computation. So and that's another example of why it's really important to really understand the languages that we use at the basic level. So there's this tool called From-C. It's an academic tool. You feed it your code. You have to put some annotations in it, but then it returns a color-coded version of your code that informs you where there might be problems, or where there might be vulnerabilities related to the compilation process. And another thing you could use is SafeInt. So SafeInt is a library that was developed by someone called David Leblanc. David Leblanc is a security programmer for Microsoft. Actually, he wrote a book that Microsoft programmers it was a required reading for a while at Microsoft. And SafeInt is a library you can use to extend, it has all the basic types, like int, double, float. But whenever an overflow, integer overflow takes place, an exception is thrown. So they're very secure. Just the problem is, just to show you how subtle the security problem is, Dietz, the person I mentioned at the beginning of this talk who studied the problem, looked at the SafeInt library and identified 43 cases in the code itself where an overflow was possible. So 43 errors of type integer overflow in SafeInt. So that just tells you how difficult the problem is that we're facing. In conclusion, undefined behavior are a reality of C and C++ and of every other language. And the programmer must be aware of this fact if he wants to produce correct and safe codes. I'm going to skip this. I wrote a book on this. Interesting because it's in French. The other thing I wanted to tell you guys about is that if you're interested in this topic, or if you're interested in other topics, there are many opportunities to study in Canada, especially for a PhD, even perhaps for a master's. But all Canadian universities, most Canadian professors are constantly looking for high caliber PhD candidates. And what many people don't know is that if you study a PhD in Canada, it's a fully funded position. First of all, you pay the same tuition as Canadian citizens. So it's not the highest tuition that's paid by foreign nationals. Exceptionally for the PhD, you pay like a Canadian, plus you get a scholarship. Everyone who studies at the PhD gets a scholarship that pays for the tuition and enough to live comfortably for the duration of the PhD. Canada is a bilingual country. You can study in French or in English. In fact, the city where I will start working this fall is a truly bilingual city. Most of Canada is either French or English, but Ottawa and Montreal are completely bilingual. So if you're interested in studying in Canada, doing a PhD, this is really something you should consider. Professors are really interested in finding qualified candidates. Thank you, and I'd be very happy to answer your questions. Am I still sharing?
Yes.
Yes. Okay, so I think I'll stop sharing the screen, and I hope you enjoyed this talk.
¿Estamos desconectados?
No, ya sé. Sí.
¿Aló?
Yes.
¿Me escuchas, Rafael?
Yes.
Ya, te doy gracias. Mira, esta charla es un poco más dura para la gente que estamos interesados en el desarrollo de software, es muy útil. Acá a las instituciones o organizaciones nos permite con este tipo de capacitación o charla o visualización tener control sobre el código fuente que tiene la organización y a la vez con esto proteger los códigos fuentes de la organización y tener una relación más de control o más de poder con respecto a las empresas que desarrollan software. En el mundo militar es fundamental tener control y saber lo que está ocurriendo en el interior. Y ahora tenemos que saber lo que ocurre en el interior del metaverso, ya que nos vamos a introducir más fuertemente a este mundo virtual.
Más pausado para que pueda escucharte.
Ya. Bueno, me pidieron que sea más pausado. Con este tipo de herramientas, nosotros podemos tener más control sobre los códigos fuentes que crean el mundo virtual. Nos permite hacer revisiones, chequeos de software en general y tener estrategias para ver la vulnerabilidad de nuestra organización y saber por dónde puede venir el próximo ataque o por dónde puede venir el próximo accidente. Una pregunta, Rafael.
Sí.
Que me dio la duda. Para el mundo IBM, que generalmente ocurre en la banca o las transacciones, ¿se ve algo diferente con respecto al overflow o otro tipo de errores que hayan podido detectar?
No entendí bien el mundo
de la banca.
De la banca. Bueno, obviamente la banca es un caso where la seguridad es muy importante. Y la banca tiene su propio estándar para la programación, para el design del software, para asegurarse que es el nivel de seguridad lo más alto.
Ya, ok. Ya, o sea, está en base a lo mismo, pero con diferentes ambientes que uno tiene que pasar con respecto para poder llegar al usuario final o a integrar la plataforma deseada. ¿Alguna pregunta, Luis?
Sí, Rafael, has expuesto vulnerabilidades en Linux. Y entiendo que eso, como el código fuente de Android es Linux, también podría ser vulnerabilidades que se presenten en Android, ¿cierto?
Claro, Android es uno de los most common source of vulnerabilities right now. Es uno de los casos donde hay mucha vulnerabilidad porque la gente baja juegos, baja muchas cosas en sus celulares sin saber de dónde viene y lo ejecuta, entonces se puede que hay muchas vulnerabilidades.
Ok, es una fuente, normalmente los juegos o las aplicaciones que están bajando puede ser una fuente de vulnerabilidad, ¿no? Porque no...
Hay cosas que tú bajas un juego y tú no lo sabes, pero está recordando todo lo que estás haciendo en tu celular y mandarlo a no sabemos dónde, y tú no te das cuenta porque la aplicación hace lo que debería hacer, pero al mismo
Claro.
tiempo está recordando o usando tu celular para hacer otras cosas.
Entonces, podemos entender que la combinación de tarjetas de crédito y videojuegos es muy peligrosa.
Claro. Yo no recordaría mi número de tarjeta de crédito en mi celular, porque yo uso mi celular para muchas otras
Claro,
cosas.
Sí.
claro.
No es tan complicado de entregarla cada vez.
Yo no tengo nada, no, yo personalmente, mi tarjeta de crédito no tiene dinero en el celular. Mejor no tener nada en el celular que sea porque lo vas a perder.
Sí, y yo digo a mis alumnos de no compartir nada en las redes sociales que le molestaría que todo el mundo lo vea.
Ok.
Sí, Alberto, muchas gracias por estas
Muchas gracias por
experiencias
invitarme.
y que nos han permitido
Gracias.
identificar vulnerabilidades, o sea, inclusive en Linux que he visto que, y claro, el celular, todos están con Android, todos tienen el núcleo Linux.
Claro.
Sí.
Y gracias
Bueno.
también por darnos unos minutos para abrir el mundo de Quebec y para el mundo de
Así.
Canadá.
Y quizás gente de Sudamérica va a venir a estudiar a Quebec, eso sería muy bueno.
No, es algo que digamos que interesa mucho en nuestros países.
Gracias.
Ya.
Sí,
Buen
muchas
día.
gracias. Vamos a estar en
Muchas
contacto, Rafael, muchas gracias.
Muchas gracias.
Agradecer tu presentación. Esto se va a compartir también con los demás colegas que tenemos acá en Perú. Muchísimas gracias. Un fuerte
Muchas
abrazo.
gracias.
Gracias a los participantes y a los que han estado atentos a esta, digamos, a esta charla que es técnica, que es dura, y sin embargo, sorprendidamente, bueno, ahí. Sin embargo, que gratamente sorprendido que hay interés en el público. Gracias.